Okay, so next is this one. You can recall that this is the only one that was left. We did not get the time to solve this one last Sunday because of that mistake in proving the binomial theorem. We however rectified the mistake afterwards, but the video stopped there. So let us start with this one today. What this one says is that we have a finite set X and M is some integer. Now on X there are real valued functions, that is functions whose domain is X and whose range is the set of real numbers, and those functions are an of X, these functions. How many functions? Infinitely many functions. In fact, one function for each integer n greater than or equal to m. So the thing that you are seeing here, it is actually a sequence of real valued functions. However, we are not going to consider it as a sequence. We still have some time to get that notion. Right now what how we interpret this thing is this. You fix an element x in X. Now once you fix X and evaluate each function an at that point X, you are going to get a real number. So after fixing X, this actually becomes a sequence of real numbers, an ordinary sequence of real numbers with which we are well familiar. So that's what the author is saying. Let X be a finite set, and keep in mind X is a finite set, and M be an integer, and for each X belonging to X, let this be a sequence of real numbers, that too not just any sequence, a convergent sequence of real numbers. That means for each element X in this set X, you are getting a convergent sequence of real numbers. So the number of sequences you will have in this situation is finite, because the set X is finite. Okay, now we have to show that if we consider this sequence, this however is not like this one. We don't have to fix X or anything, because what we are doing here is we are taking the sum of all the values of the function an as X varies over X. So we are considering this sum over the finite set X, and that of course is a real number. But again we are getting a sequence of real numbers where of course n would start from m, where m is some integer, and then we take higher and higher values of n, changing the function in the process and getting infinitely many sums. Each of them is a real number because the sums themselves are finite. Now we have to prove that this sequence of real numbers is convergent. That means it has a limit, and its limit is equal to this sum of the limits of anx as x varies over x, and this limit of course is again a limit of a sequence of real numbers. So we have to prove this, and there is a hint. We have to induct on the cardinality of the set X, because X is a finite set, its cardinality will be a natural number, so we can apply induction on that. And we have to use theorem 6119 part A. 6119 is our familiar limit laws that we already have proved and we know well about it. So that means, looking at this, you can see that we have been able to interchange limit with finite sum. So the author writes, thus we may always interchange finite sums with convergent limits. However, things get trickier with infinite sums, which we have not considered yet. We are going to consider it next. In the next section, which we will do today itself. See exercise 19.2. Is it exercise or example? Exercise. 19 to 11. We still have a long time to get to that, but we will see. Okay, so let us now prove this by induction on the cardinality of X. So the base case will be the one where X is the empty set. Solution when X is the empty set, the sequence an of X as X varies over X. This is the nth term of the sequence where n itself varies from m and it then increases without bound. This sequence is the constant sequence, all of whose terms or all of whose elements are 0. Why? Because each sum will be 0 by definition of sums over finite sets, because the set over which you are considering the sum is empty. So by definition this sum is actually not exactly by definition also, it comes from those basic properties of sums over finite set. You know what we are talking about here. So each of these sums will be 0, so we are getting a constant sequence of zeros which of course converges to 0. Also the sum is 0 or has value 0, same meaning. Here also, because the set over which you are considering the sum is empty, so this sum is also 0. The thing that we have said here, which converges to 0, means this left hand side is 0 when X is empty set, and that right hand side is this, which is also 0. So the claim is true when the cardinality of X is 0, or the same thing when X is the empty set. This is the basis for our induction. Now we make the induction hypothesis. Now let the claim be true for any set of cardinality n, where n is some natural number. You have to understand that although we are mentioning only about the set in this induction hypothesis, but those functions and everything, that general setup is there in the background. Okay, those things are included because otherwise the claim does not have any meaning. Now, to carry out the induction step, we next have to look at a set having n plus 1 elements, or cardinality n plus 1. Now, let y or z, anything you can take, be a set of cardinality n plus 1. We also have to assume consider the other things that come with Z. For each Z belonging to Z, let us take some, use some other name, Bn x and varies from m to infinity, be a convergent sequence of real numbers. Okay. Okay, so that means now we have to prove the claim for Z and this sequence Bn. First of all, we notice this. Since Z is a non-empty set, because its cardinality is n plus 1, in the least possible case where n is 0, then also Z has exactly one element, so it is in any case non-empty. We can choose an element, say Z naught, belonging to Z. Then if you remove Z naught from Z, that subset will have cardinality n, because you are removing one element. In fact, that we have proved in one previous in the section 3.6, which treats finite sets. There we proved this fact, which however is so natural that there is no need to actually mention that result. We can just simply then write this. Then this set has cardinality n. So we can apply the induction hypothesis on this set. So by the induction hypothesis, what shall we have? This thing we have, limit as then approaches infinity of this sum Pnx. Because we have Z, so let the variable element be denoted by z. Minus z naught is equal. I think it's better to write it not necessarily in one line but like this. Okay. Now, in applying the induction hypothesis and hence in writing this equation, do you see what has gone on in the background? Our finite set now is this, which has been obtained by removing this z naught from the original set z or c. Now the sequence of functions that we were talking about there, this sequence of functions is still there. Oh, so here also I made that mistake. No? I need to write z here, otherwise that does not make sense. This sequence is still there, but the things we have inside the sequence, the terms, no longer are functions defined on the entirety of z, but rather on this subset. Okay. But that is not a problem, because you see, we are actually considering everything, almost everything that we have written here, except at z equal to z naught. Only for that value we don't have anything here, or we are not considering that value. For other z values coming from capital Z, we have all the things. For such z's also, this is a convergent sequence of real numbers. We are just simply not considering the case z equal to z naught. That's it. So we are able to write like this. These fine details, of course, we don't make them a part of the solution. So simply put, we have this now. Okay. Now it's time to use two things. First of all, we need to somehow link this sum with the similar sum where we don't have this subset but we have the entire set Z. So there the basic properties of sums over finite set come. Now by, and that thing is this proposition seven 111 E, part E. We have what? Summation Bn of Z as Z varies over Z is equal to Bn of Z naught plus summation Bn of Z where z is coming from z minus z naught. You understand what we have used here, that writing a sum, it's that thing, no? Summation x union y is equal to summation over x plus summation over y, where x and y are disjoint sets. And here this is also a sum. This after all is the value of a sum. What sum? Shall I write that? In fact, you can understand what we have here. If we decided to write this as a sum, we would have written summation bn of z, where z is coming from the singleton set z naught, plus this summation. Since this singleton set and the set obtained by removing z naught are disjoint, so we can use this part E of this proposition to write this sum as a sum of two finite sums. Okay, so that is one thing. And now next we use the limit laws on this equation itself. And doing that, we need to also mention one more thing. This is true for what values of n? In fact, this is true for all. Keep in mind that the integer n here is not changing. The elements, of course, are changing, they are varying over these sets, but the n is fixed. So we need to mention for what integers in this equation is true. In fact, this is clearly true for all n greater than or equal to m. That means for all possible n in this situation. Hence, by limit law, which is what is the number of that thing? Theorem in 6119. Yes. A. We have limit as n tends to infinity summation Pn z as z varies over the set z is equal to limit n tends to infinity Pn z naught plus z, where here z belongs to this. Okay, now you may be wondering about one thing. It is given that B and Z is a convergent sequence of real numbers for each Z in capital Z. But does that automatically tell us that this limit itself is it exists? For example, what I am trying to say here is that here in this equation n is changing. For example, you can take n equal to m, you get one such equation. you take n equal to m plus 1, next you get another such equation, and in those equations you have these terms which depend on n. So they are terms of a sequence. Now whether that sequence is convergent, of course that is convergent, and that also comes from the fact that we have this theorem and these are finite sums, okay, and that is why that is convergent. So we have this, and so now what we can do, we can use this thing, and that will give us, that will help us continue this calculation. So this left hand side, it remains like this. On the right hand side, what we do, the first term of course we keep it as it is, p n z naught, plus here what we can do, we can take, for the sake of clarity let me write here, the limit inside. So in this step we have just used this one, that's it. Next, this will be equal to let us complete this calculation first, then I will tell you that whatever I have said just now is not entirely correct about the convergence of this, but we are coming to that later. Let us first complete the calculation. Now this is equal to, oh, so I need, okay, I need to write this itself as a sum, this first limit. Which of course we can do because this is a singleton set, so the sum will be this. In fact, here also we could have done that, but let's just not waste time on that anymore. Summation so we can again apply that proposition 7.1.11e in the other direction and write in place of this sum of two sums, this single sum. Belongs to the union of these two sets, this singleton set and its complement in Z, which is Z. Okay, now I am coming to that question of how are we actually taking the limit and exactly how are we using theorem 6.119. The thing is that these two sequences, you watch this. This is a sequence where n is varying from m to infinity. Its nth term is the value of the function bn at z0. And there is that other sequence, which is this. These two sequences are convergent. Why? The first sequence is convergent, and that comes from our hypothesis itself, because that is the setup. According to how we have considered everything, the first sequence is convergent. Okay, so this is a convergent sequence of real numbers. This sequence is convergent, and that is coming from the induction hypothesis, what we assumed before carrying out the induction step. So these two are convergent sequences of real numbers. So their sum will also be convergent, I mean the sum of these two sequences, and its limit, the limit of the sum will be equal to the sum of the limits, and the limit of the sum is this. Because if you take the sum of this and this, then by your properties of finite sums, that equals this, which also is an nth term of a sequence. So that sequence is convergent, and this convergence is coming from theorem 6.1.19. Okay, so that is why this is convergent. It's not because this is the finite sum and this is convergent. So what I said just now is not correct actually. The convergence of this left hand side, or in other words, the existence of this limit is coming from the fact that we are dealing with convergent sequences. So their sum will be a convergent sequence, and its limit will be equal to the sum of the limits of these two sequences, and that's what you see here. Sum of these two limits. Okay, and after that, of course, here we have used the induction hypothesis, and then we were able to rearrange things and again use that property of sums over finite set to finally get something like this. And this is where the induction is completed. It's complete. This completes the induction. And proves the claim. And that's just it. That is our solution to the last exercise here in this section, and so the section is finally over. Now we will move on to the next section, infinite series. So this is the next one, 7.2. Infinite series. So Professor Tau starts. We are now ready to sum infinite series. So first of all, he starts off with the definition of an infinite series. This is the first item, so will be 7 to 1, and it's a formal infinite series. just like we had a formal definition of a finite sum, like that we have a formal definition of an infinite series, and in fact that itself is called a formal infinite series. And this thing, however, is not that much complicated and convoluted like the definition of a finite series we saw, where we in fact had to use the principle of recursive definition very carefully and all those things. This one is pretty straightforward. A formal infinite series although infinity is a concept or a notion that it's difficult to wrap our heads around, but sometimes finite situations are more complicated than infinite situations. A formal infinite series is an expression like this of the form. I do not want to lose any word that Professor Tao has written, because maybe there is something hidden which I am not getting at the moment. An, where n varies from m to infinity. Do not immediately attach any meaning to this symbol other than what is being said here. By this definition, a formal infinite series is a symbol which looks like this. Okay, now we are going to say what these parts of the symbol are, where m is an integer, usual things, where m is an integer, and let me write like this. This is an is a sequence of real numbers. So when I say don't attach any extra meaning to this symbol, what I specifically mean by that is it looks like we are taking the sum of all the terms of this sequence, because the notation suggests something like that. However, do not interpret it like that. You just treat it as a formal symbol and that's it. Slowly we will attach more and more meaning to it. In fact, the author has written here, in place of this exact part, he has written where an is a real number for each integer n greater than or equal to n. But that is of course equivalent to this thing. You can clearly understand. We sometimes write, so whatever I said just now, don't interpret the series as a sum. The next notation, which is a slightly less formal way of writing the series, actually suggests that. However, in spite of that, here also do not attach your own meaning to this next expression that we are going to write. We sometimes write, I need ink. as this. In spite of how this looks, it's not a sum of all the terms of this sequence, because such a thing has not been defined yet. And that's why in the next paragraph, so this is what the definition is. The author writes, at present, this series is only defined formally. And that is why do not think of these plus signs as actual addition. They are just part of this entire composite symbol denoting the series. We have not set this sum, although the author of course is calling it a sum, but it's not an ordinary sum in the usual sense. We have not set this sum equal to any real number, which we will do next. That's the thing. We have not set this sum equal to any real number. And the thing that we will see next, that is one way of attaching a real number to this series, which we are next going to call, after we have that definition, the sum of the series. However, that is not the only way. If you already know a little bit about these things, you know that this kind of series sometimes have a sum, sometimes they don't have a sum. Those series that have a sum are called convergent series, just like how we have convergent sequences. And those that do not are called divergent series. However, there are ways of attaching real numbers to even divergent series, which of course would use some definition other than what we are now going to see. That is the summability of infinite series, summability theory. The notation is of course designed to look very suggestively like a sum. The notation I am not very sure about this, but in some parts of theoretical physics, there are some infinite series or some sorts of infinities occur, which the physicists successfully, not just simply as a game, they successfully attach some real numbers to those infinite series, thereby getting rid of infinities, which of course have no physical meaning, in their theory. So getting rid of those infinities, there is a very systematic procedure for doing that, and it's called renormalization. I'm saying all these things very vaguely because I don't know, but I keep on hearing these things here and there on the internet, so I wanted to tell you this. You may be interested. Designed to look very suggestively like a sum. but it's not an actual sum. But it is not actually a finite sum. Because of this dot 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 ellipsis symbol. Okay, to rigorously define what this series actually sums to, we need another definition. And then comes this next definition, which is convergence of series. And in fact, in this definition, we will see why we are denoting a series itself using this kind of notation, which makes it look like an infinite sum. Strictly speaking, a series is an object which is a symbol made out of an infinite sequence of real numbers, and we are now going to attach a sum to it. Let and that's just it. But the nature of this definition will justify this notation. Let this be a formal infinite series. So we understand that this is an infinite sequence of real numbers, so all those things are there in this included in this statement itself, that this is an infinite series, a formal infinite series. First of all, for each integer n greater than or equal to our lowest possible value of n, m, we define something called the nth partial sum, Sn, by this formula, this definition. Sn means this finite series. And we already know what finite series is. That's why we had that previous section. So that is our finite series. Of course, Sn is a real number. That is, of course, something obvious. Now, if the sequence Sn, where n is varying from m to infinity, is convergent. To where some real number L as n approaches infinity, then we say that the original series itself is convergent and has capital L as its sum. Infinite series is also convergent and converges to L. We say that the infinite series is convergent and converges to L. So that means we see that the convergence of an infinite series is just the convergence of a sequence of real numbers whose terms are the partial sums of the original series. And we also express these things like this. We also write L equal to this series to express this fact that the series is convergent and it converges to L. That fact is expressed by this equation. Okay, this equation just simply means that thing. And what about that calling L as sum and say that L is the sum of the infinite series? Yes. Okay. And what happens if the sequence of partial sum does not converge? If this sequence not if this is not convergent, or in other words divergent, then we say that the infinite series itself is divergent, or it diverges. and when this happens, we do not attach any value to this like L. But even in this case, in some theories of summability, we still attach value to this thing. You may have already seen something on the internet like this, which looks like this. This type of thing, and Ramanujan's name is attached to it. Although it is extremely misleading, the way this thing is put is extremely misleading. But more or less it's like that thing, what I was saying just now. That even in cases where it is not ordinarily convergent according to this definition, there are ways of meaningfully, in some sense, still attaching real values. The equation that I wrote just now, that is extremely confusing, and it's a deliberate misinterpretation of something. Okay, if you know about it, you know. We will see all these things when we study complex analysis someday. Okay, so divergent, and let us complete the definition now. And we do not assign any real number to the real number value to the series in this case, and in this case we do not assign any Okay, let us now come to the question of why the notation looks like this or like that thing. Can we justify that to some extent from this definition? So what this definition says is basically this. You have a formal infinite series, which is this. Or something like this, where an of course is a sequence of real numbers. Now, according to the definition of the sum of this series, say it is convergent, then it is the limit of the sequence of partial sums where what is Sn? Sn is, if we write like this, which is easier to understand, then Sn is simply this. Am, in fact, in this general setup also it won't be very difficult to understand. M plus 1 plus like this. An. Now your n is itself starting from m, right? Because your sequence of partial sums looks like this. So what this limit tells us is that if we write the terms of this sequence out, then we are considering a sequence whose terms one after another look like this. Let me write one more. So that means each term is of this sequence of partial sums is obtained by adding one extra term from the original sequence An. And if a limit of this process exists, that limit has been defined to be the sum of this series L. So it's like adding more and more terms. So in the limiting case, it looks like we are adding all the terms of the sequence. So that is why the notation looks like this. It tells us, it suggests us what we are doing in this limiting process. And you can of course understand why these sums are called partial sums. These sums don't have everything, all the terms of the series in them, but only a part of them. So that is why these are not the total sum, these are the partial sums. And that's why the notation looks like that, because that's the meaning of this convergence, or rather the meaning of this limit. Okay. Remark. Because we have defined the sum of an infinite series whenever it exists to be the limit of a sequence, so we know that whenever it exists, it is going to be unique, because limits of sequences whenever they are convergent are unique. So that's what this remark says. Note that proposition 617, which in fact here we proved that uniqueness of limits of convergent sequences of real numbers, shows that if a series converges, then it has a unique sum. So it is safe to talk about the sum, not just a sum of a convergent series. Of a convergent series. If instead of this definition you wanted to use maybe some other definition where you are not necessarily considering, say, sums, you may, I'm just simply for the sake of argument saying this, that you are, for example, considering something else like this, say some other operation, say minus some other operation, then of course these sums and their eventual limit when it exists will not suggest you to write the corresponding object like a sum like this. Then the notation will change. So the notation has been designed to suggest that we are dealing with sums. next we consider one example which illustrates these notions. And in this example, we are going to consider two such formal series. Consider the formal infinite series where an is 2 to the power minus n and that integer m is 1. So more informally, less rigorously, we also write the series like this. Unless one knows these things, that the right hand side is also actually simply a symbol, a formal expression, all kinds of confusions arise. And unless we know the exact meaning of this, people tend to think of an infinite sum where infinitely many real numbers are being added together. There is no such thing. Okay, whatever things we have seen so far, or the things that we are still going to see in future, in normal mathematics, that kind of infinite sum has no meaning. But an expression like this can be devised which gives some meaning to the notion of an infinite sum in the sense of this limiting process and the resulting limit. The partial sums n equal to 1 to n can be verified to be so we are considering 2 to the power minus n, so it will be, it is minus n, not plus n. Okay, 1 minus 2 to the power minus n, and this of course you can verify either by induction on capital N, or you can use your geometric series formula, finite geometric series formula. Since this thing converges to, we already know about these things, we have already seen in the theory of sequences, as n approaches infinity, has the sum one, which less formally we also sometimes write like this. This is something that you probably have already come across in your schools itself. When after introducing finite geometric series, then from that you naturally have this infinite case also. You learned something like this, that if the common ratio of the geometric series, infinite geometric series, has its absolute value less than 1, then there is a sum which looks like, there is of course a formula. Now in its place, in particular, this series is convergent. Okay, in particular, this series is convergent. Now in its place, if we consider this next series, now consider the formal infinite series 2 to the power n, where again n varies from 1 to infinity. And so on. In this case, the partial sums are these, which again can be either established by induction or you use your finite geometric series sum formula. We can easily verify that the sequence is unbounded, and hence it cannot be convergent, because we already know that every convergent sequence of real numbers must be bounded. So the series itself is divergent. So this is an example showing a concrete convergent series and a concrete divergent series. Now we address the question of when a series is convergent. Now we come to the theoretical question of how to know that a given series is convergent, or what are the conditions for convergence. And we of course have a result for that. The following proposition shows that a series is convergent if and only if its tail can be made as small as we want. Technically speaking, only if the tail of the sequence, its tail or tail of the sequence, because this is not a mathematical technical term, we can say tail of anything. Looking at the statement of the next result, you will understand what we mean by tail. Sequence can be made smaller than epsilon. What is the author writing? Is eventually less than epsilon. For all epsilon greater than 0. Now we come to the actual statement. But before that, another refill. This one does not have any name. Let summation an, where n varies from m to infinity, be a formal infinite series, then this is convergent if and only if, in place of if and only if, you can oh sorry, this is not a definition, why I keep forgetting this is the proposition. Okay, you cannot just simply write if, because that will be half of the proposition. If and only if the temperature actually takes away the ability to concentrate and in fact understand what is going on. Then this converges if and only if for yes. For every positive real number epsilon, there exists an integer n greater than or equal to m such that the sum of an as n varies from anything to anything, say p to q, is less than or equal to epsilon for all p and next we need to say what these p and q are. For all integers p and q greater than or equal to n. So the series is convergent if and only if these finite portions can be made as small as we like, starting from some stage, and these are tails of the series. So that is the proposition, and its proof of course we will see in the exercises. Seven to 2, so that means before this there is another one. Okay, this proposition by itself is not that handy. I mean, you cannot easily use this proposition because usually it's somewhat difficult to calculate these sums in practice if an actual formal infinite series is given to us. However, it has theoretical importance because from this proposition there come out a number of corollaries which themselves are much easier to apply when we are dealing with actual series, and which are important from the point of view of that application. They are highly applicable. Because it is not so easy, yeah. Because it is not so easy to compute the partial sums. Partial sums means in this context these sums are being called partial sums, although they are not technically the actual partial sums of the series. These they have in fact also mentioned that by partial sums they mean these sums in practice. but these next results make it worth studying. However, it has a number of useful corollaries. For instance, this next one. Seven to 6. Zero test. It has a name. Languages like that. Let be a convergent series. There is a formal infinite series which is convergent in the sense of our definition of convergence. Then the sequence an itself must converge to 0, and that's why it's called the zero test. This limit should exist and should be equal to 0. Keep in mind, it's only in one direction. If the series is convergent, then the sequence of its terms converges to 0. The converse, however, is not in general true. To put it differently, if the limit either does not exist or exists but is non-zero, then our series is divergent. It's not convergent. And this equivalent formulation of this zero test is the one that we use to prove that some series are not convergent, because it's very easy to compute the limit of the sequence of the terms in the series. If either it does not exist or it is a non-zero real number, then you can immediately say from this corollary that the series is not convergent. You don't have to go back to the actual definition, look at the partials and see whether that sequence converges or not. So this becomes a useful test for non-convergence of certain series. Next, to illustrate these things, we have this next example. The sequence an, wherein of course varies from m to infinity, where in place of m you can take any integer, whose all the terms in the sequence is 1. So it's a constant sequence 1, 1, 1, 1 and so on. We know that this sequence converges to 1. Since the sequence converges to 1 as n approaches infinity, the corresponding series will be divergent because this limit is not 0, it is 1. Although you don't have in here, but what is the author taking? In place of m he is taken, you can take anything. This is in this case, since it's very easy, I want you to go to the partial sums of the original series and you will see that the sequence of partial sums is just the sequence of positive integers, which of course is not convergent due to the fact that there are many reasons, but one of the easiest way to see why the sequence of partial sums of this series, which is this sequence, is divergent, is to notice that it's an unbounded sequence. So it is not divergent. So directly you can also see like this, but sometimes directly working with partial sums becomes much harder because the partial sums themselves may be difficult to compute. So in those cases, this corollary may be helpful. Is a divergent series, same thing. Note that, and the author also reminds us that the original sequence is a convergent sequence. So the sequence of terms 1, 1, 1, 1, that is convergent, but if you use them to form this series, the series becomes divergent. And that is why a convergence of a series is a totally different thing than convergence of a sequence. Because when one encounters these objects, these mathematical objects for the first time, looking at this expression, sometimes one tends to forget that one is working with a series and not with only these terms, that is with the sequence an. So in those instances mistakes happen. So we should be careful about this distinction. Similarly, thus this other sequence whose nth term is the nth power of minus 1 is not convergent. Unlike this case where the limit at least exists, it is a non-zero limit, that's a different matter, but it exists. In this case the limit does not exist at all, is not convergent. So but the conclusion is same. So the series is also not convergent or is divergent. Now, if you can recall a very old episode where we were in fact starting all these things. In the beginning of this text, there is a part which focuses on some issues that if one uses the rules of calculus blindly, then one would get nonsensical results. In those questions or in those erroneous things that we got back then, this one was one example. Considering this series is the same as considering this thing, no? If you remember, we somewhat whimsically, without knowing about anything, tried to calculate the sum of this series back then. So we applied several methods to do that. For example, we did something like this, which gave us the conclusion that the sum is -1/2, or we also tried to make sense of the series like this. Giving us also the result 0, and something else also we did. So back then we asked the question, what went wrong in our calculations and in our arguments. So the thing that went wrong here, now we know, is that we are assuming while doing all these things that the series actually has a sum. It does not have a sum in this usual sense, or at least how we think a sum should be. So that is why this kind of nonsensical things were happening, and we in fact did not have any justification for doing these calculations. I mean, we are dealing with quantities which we know nothing about. So how are we suddenly grouping the terms like this, or for example taking -1 common out from infinitely many terms? So those things actually do not make sense. They will make sense in specific situations. We need to identify these situations, and then in those situations we will actually be able to carry out such computations. But there will be, those computations will be backed up by theory, not just some whimsical calculation like this. And this you can clearly see is nonsense. So this series is divergent. So we can see that in certain cases we can use the zero test very nicely to conclude that some series of real numbers are not convergent. Next comes the question of the converse to the zero test. The converse is not true. If the sequence does not converge to 0, then the series may or may not be convergent. Simply the limit of this sequence not being 0, that fact alone would not decide anything. So the situation will depend on the specific series itself. It depends on the series. For instance, we will have to wait a little to get to this result, but we will see. This series, whose nth term is the reciprocal of the positive integer n. This series also has a name, it's called the harmonic series, is not convergent. Although you can see that if you take the limit of the nth term, that limit is 0. So the converse to the 0 test is not in general true, and this is an example that shows that the converse is not true, a counter example. Despite the fact, we need to mention that also. This converges to 0 as n approaches infinity. Let us next look at another definition which gives us a different type of convergence of a series, where we are not actually using some other ways of defining the sum of the series, but we are going to call a series absolutely convergent if a related series is convergent. Now this notion of absolute convergence is not just simply an ad hoc notion, but you will see that series which are absolutely convergent are the type of series where in fact you can change the order of the terms in any manner you want. The behavior of the series will not change. If it is convergent, it will remain convergent with the same limit, and if it is divergent, it will remain divergent. So let's now see the definition. Let this be a formal infinite series. We call the original series absolutely convergent. it's a very peculiar fact that this definition of absolute convergence, or in fact the notion of absolute convergence, is very intimately linked to interchangeability of the terms of a series without affecting its behavior. Absolutely convergent if the series this, where we are using the absolute values of the terms, hence the name absolute convergence, is convergent. So that means if this series is convergent, then we call this series absolutely convergent. Note that simply from the definition itself, we don't know whether an absolutely convergent series itself is in fact convergent in our usual sense, but that is a fact. We will prove that. In order to distinguish between what? Ordinary convergence from its absolute version we call the format, that is ordinary convergence, also conditional convergence. That means if a series is just simply convergent, then that is also sometimes we say that the series is conditionally convergent. But if we are saying absolutely convergent, then of course that means this series is convergent. So what I was saying about this and changing the order of the terms is like this. Say you look at this series. We have already seen this in one example now. It has the sum 1 that also we have seen. It turns out that this series is absolutely convergent. That is just a simple fact, because here all the terms are positive real numbers. So in place of this series, if you consider this series where you replace all the terms with their absolute values, then nothing changes actually. You are getting the same series back, which is convergent. So, and it has the same sum. Okay. The fact is that since this series is convergent, so the original series is, by our definition, absolutely convergent. Now, by the result that I was talking about, that allows us to write the terms in any manner we want. That is, in place of this series, if you write like this, and have another series, say that is, you interchange consecutive terms. This also is a convergent series and it will have exactly the same sum, which is not a trivial fact. In fact, you just think about it. What does this equation tell us? This equation tells us that if one considers this sequence, then this is a convergent sequence of real numbers and it converges to 1. This equation on the other hand tells us that this other sequence is also a convergent sequence of real numbers with the same limit. Okay, and it's nothing obvious, which however is a very useful fact. Due to this fact, we can change the order of the terms of an absolutely convergent series without altering its behavior. And if you have a series, okay, so that's about absolute convergence. Now, if you have a series that is simply convergent but not absolutely convergent, such series also exist. Otherwise, this definition would be meaningless, would be valueless. Such series, however, have such bad behavior that you can rearrange the terms of a conditionally convergent series which is not absolutely convergent to make its sum any real number, and also you can make it divergent by a proper rearrangement of the terms. So non-absolutely convergent series which you may have, they behave as wildly as possible. That also we will prove at one stage, which I think is one of the exercises. Okay, now next we come to a proposition which tells us when a series is absolutely convergent. This is test for absolute convergence, or well, not exactly when a series is absolutely convergent, but what happens when a series is absolutely convergent. Let this be a formal infinite series that is absolutely okay. So they are going to first of all write infinite series of real numbers. Next, if this series is absolutely convergent, then it is also convergent. That is the result. Then it is also convergent, or using our other term, conditionally convergent. And there is a statement about its sum also. And furthermore, so in another line, in this case we have the triangle inequality. we are calling this next thing triangle inequality because it looks like ordinary triangle inequality. The original series being absolutely convergent means the right hand side is a convergent series. So it will have a sum which is a real number. The proposition is saying that then this series that you see inside modulus, that is also convergent. That means the original series is convergent, or in other words conditionally convergent, and you have this relationship between their sums. Its proof also we will see in the exercises. However, I forgot to write in which exercise, but we will see. Instead, let us end our video with this next remark. The converse to this proposition is not true. The proposition says that every absolutely convergent series is conditionally convergent, but there exist conditionally convergent series which are not absolutely convergent, and that is why the definition of absolute convergence is worthwhile. It's a special thing. Is not true in general. There exist which are not absolutely convergent. There is one very elementary example, but we will see that later. See, is it example or exercise? We will see. Okay, right now I have written EX here, so I am not sure. 7.1.7.2 13. Most possibly it's an example. And there is one more. This next remark, we consider the class of conditionally convergent series to include the class of absolutely convergent series. Although we are saying that we are distinguishing between conditional convergence and absolute convergence, that may make you wrongly think that these two notions are disjoint, in the sense that when one happens, the other cannot happen, and vice versa. No, that is not true. Conditional convergence simply means convergence. That's it. Absolute convergence is a special type of convergence. That's the thing. The class of conditionally convergent series is considered to contain the class of absolutely convergent series as a subclass. Thus, when we say this series is conditionally convergent, we do not mean that the series is not absolutely convergent. Conditional convergence simply means convergence. It does not stop a series from being absolutely convergent. Conditional convergence means being in the class of conditionally convergent series. There, inside of it, sits the subclass of absolutely convergent series. Now, your series may lie here or it may lie here also. Simply saying that sigma is in this class does not tell you whether it is outside ABS or inside ABS. If you want to say something like that, you have to mention it specifically. So that's why the author write, which I am not going to write. So if one wants to mean that this series is conditionally convergent but not absolutely convergent, then they have to write that explicitly or say something like this: this is only conditionally convergent. Then it would mean that it is at the same time not absolutely convergent. That means it is lying here. Okay, so with this I end this video. I think it has been rather long. Anyway, if you have any comments, you can make those comments in the comment section below, or you can mail me at my usual address. The link will be there in the description. And this coming Tuesday we are again going to do number theory. So with that I sign off. So see you on Tuesday with number theory, and until then, this is me, Lucifer, from the mathematical room. Have a nice night.